think about and learn more about. So I'm Kenrick Duru, for those of you who don't know, one of the co-leads of RICMAR, and very excited and happy to introduce our guest speaker, Dr. Marianne Bitler, who's a professor in the Department of Economics at UC Davis. And she focuses on the effects of government safety net programs on disadvantaged groups, economic, demography, health economics, public economics, and economics of education. And I'll say I know her because she also is part of a CDC funded network looking at natural experiments in diabetes. And I had the chance to hear her give a great talk on Friday. So this is two talks in 4 days, but looking forward to this one now. So Marianne, please go ahead whenever you're ready.
It's great to be here, and please, it's hard to monitor the chat and talk, but please just ask questions if you have questions, and I'll just go ahead here, okay? First of all, I wanted to offer you a couple really good references. So this book, Angrist and Pischke, is aimed at a master's audience, but it's got what I think is really good intuition, and I use it in my applied econometrics PhD course to help you with the intuition sometimes, because sometimes the books that are the best for sort of learning the, X prime, X inverse, et cetera stuff are not the best for giving you intuition behind what's going on. And then the NBER is the National Bureau of Economic Research. A lot of economists who do empirical work are members there. They put out nonpartisan research, but importantly, they also do methods lectures. And so this is a slightly older set of lectures, but it's, I think, pretty good at the basics. Not that much has happened since then that isn't, super fancy stuff on the top end. And also, if you're interested in weak instruments, which we'll get to, there was a whole set of lectures about weak instruments, okay? And there are lots of other references, but these are things that are fairly accessible, which I think can be helpful, when you don't have the time to just set aside a couple months to learn something from top to bottom, but you're trying to sort of squeeze it in while doing research, okay? So I'm also going to use a lot of jargon, so stop me if there's something that you don't know what it is, and I'm never sure. There's this great thing that a friend of mine made for the translating economics to sociology. And so I know that, or at least I suspect that there's a diverse group of people with different training. And so this is just words I'm going to use. I think that you probably all know all of them, but in case you don't, I'm going to go over these three things here a little bit more in detail, okay? But, just to make sure we're all on the same page, when I'm talking about internal validity, I mean, what you'd get from an experiment. That's the Rubin sort of counterfactual model is the mindset I'm coming at this from. And external validity is this question of, do these estimates that you have extend to other settings? And so experiments are great because they give you fantastic internal validity, as long as you didn't implement them wrong or get really unlucky. But they may or may not be good for external validity because often you're sort of constrained in terms of who you can get to cooperate with you in doing an experiment. And there's a great paper on this that looks at energy use, experiments to tell you about how much energy you use. And the folks who looked at this found out that that the effects were bigger for early adopters of something like that. So that's an important consideration even when you're using experiments, okay? And there are two other things that can cause problems that I'm not going to talk about today, measurement error and the wrong functional form that I'm sure you're also all aware of. Some of these can be also helped with IV, but I'm mostly not going to focus on that, okay? So just to start us off, in the back of your head, you should have the potential outcomes model and experiments. So in this world, Y is not a random variable anymore. Y is something where there are two possible conditions, and the thing that varies is treatment. So treatment is random, but because it's controlled by you, the experimenter, but the outcomes are not random. It's just that you have two different outcomes. You have an outcome that you would experience if you were untreated, and that's Y0I, when DI, which is the dummy for being treated, is 0, and you would have an outcome if you're treated. And they're deterministic, but we only see one of them in the real world. If you're treated, we only see D1I, and if you're not treated, or Y1I and D1I, and if you're untreated, we only see Y0I. So then person I's treatment effect is the difference in these two things, and your value that I see in the world is your outcome if you're untreated, plus your individual treatment effect times the dummy for whether or not you're treated, okay? And in this setup, it's really a missing data problem. So you never see a person in both states, okay? And this is why you can't, draw inference about this without making a bunch of assumptions, okay? So to put this into a concrete setting, Y could be health and D could be private health insurance. And the problem is we never see someone who's simultaneously insured and not insured, okay? Something I'm also going to point out here is in this more general version of this model, the treatment effect, this Y1I minus Y0I, is actually varying at the individual level, okay? A lot of the times we pretend that that's not the case and we're just estimating a beta that's the common effect, but really what you should think of underneath this, if you come to this from the sort of IV economic slate perspective, is that there's really an individual level treatment effect and we're calculating averages of it for particular populations, okay? So what can we see if we use observational data? Well, if we have observational data, we have people who are treated and we can figure out the mean effect for them. That's this piece. And we can figure out the mean effect for people who are untreated, and that's this piece, okay? And I can rewrite this in this way. So I can rewrite this as one term that's the difference in the individual level treatment effect between treatment and control for the people who are treated, plus the same difference between in the control condition for people who are treated minus people who are untreated, okay? This first piece is the thing that we want. It's the individual level treatment effect averaged over everybody that's treated. And then, we can't see all these pieces because of this missing data problem. We never see this piece here. We never see what the people who were treted's outcome would have been in the control condition, okay? So we want to estimate this thing, and we have to figure out a way to get rid of this other thing, this difference here, which is the selection bias, okay? So this thing, if this thing averages out to be 0, then we are estimating something that's unbiased for the average across the people who are in the treatment group, okay? This is all saying this in words. So if I did this as an example of my health insurance, private health insurance example, which is going to be a running example here, we think that there might be selection bias. Why? Well, people who can't afford group health insurance might have worse health than people who can afford it, right? And so those people might have worse health even if they didn't have health insurance. And so the selection bias term here, this difference between your expected outcome if you didn't have health insurance and you bought health insurance when we see you, minus the expected outcome for the people who can't afford the health insurance, we don't think that thing is going to be 0, okay? It's going to cause a bias. So that's what we're trying to get around. And how does randomization help us? Well, if we randomize DI, then there'd be no reason for this selection bias term not to be 0, right? Because if I randomize DI, there shouldn't be any correlation between Y0I or Y1I and DI. Okay, and so that's exactly how experiments get us around this fundamental causal challenge. Okay, and so that's just the setup that I'm thinking of behind all of this, because I think that this is an easy way to think about how to extend this to instrumental variables. So what are instruments doing? Well, sometimes we actually run experiments and use the assignment to treatment status or the offer of treatment as the instrument. Or we're looking for things out in the world, natural experiments that give us something like an instrument that's quasi-random, that is going to only affect the outcome Y through its effect on D, okay? So now I'm gonna go through some stuff about this, okay? I'm gonna skip that one because we don't really need it. So there is this assumption that when we run this experiment, we ensure that the error term and D are not correlated, okay? We have this assumption that we call a conditional independence assumption, but it really just means, there's nothing in the error term that's correlated with treatment status, okay? That's why in an experiment, we get this thing we wanted, all right? So what are problems out in the regular world where you just want to look at people who are insured? Well, sometimes there's omitted variable bias. So some other factor is associated with both the independent variable D and the dependent variable Y, and it's not controlled for. So for the example that I'm giving you, income, employment, all of those things are associated with group health insurance. And so if you don't adjust for them, you might be missing things when you try to understand how health is correlated with private health insurance. There can be simultaneous causation or reverse causation in this case. If I have bad health and I can't work, then maybe I can't sign up. This should say can't, but it could also be can sign. I'm more likely to sign up for health insurance. So there's something about past health causing health insurance and not health insurance causing health. Sample selection. This is another one where IV can help. So if you're somehow missing people systematically from your sample who have certain outcomes. So selection on your independent variable is okay, it just causes noise, but selection on your dependent variable is a problem, okay? So if we were going to look at people who are at age 80 and we wanted to understand how having had health insurance at age 45 mattered for health, some of the least healthy people will have died, and that would cause sample selection if we didn't include them into our observation. And then, as I said, IV can also help with classical measurement error. Okay. So I think a useful thing to think through when you're trying to decide how big a problem this omitted variable bias is to try to sign it, okay? To try to think, what is the bias that this is causing? Is this causing my estimates to be biased upward or downward, all right? And so this is a bunch of math, but the point is the sign of the bias depends on the correlation between X, that's your variable that you care about the effect of, and the error term, okay? And, there's some important features about omitted variable bias. It doesn't go away with more data. The magnitude is a function of the correlation of the omitted variable and X. The direction depends on the sign of this thing. And if you have other covariates in there and they are correlated with the error term, it's also a problem, okay? But it's always worth thinking in your own data about which way the bias would go when you're trying to evaluate what you found. So here are a couple examples of this. Education and wages. This is every labor economist's favorite example in the whole world. Every labor economist wants to know the returns to schooling, or how much more do you earn for each additional year of schooling. Whatever you want to call skill, whatever you think is rewarded in the labor market, it's rarely something that you have in the data that you get that you want to look at this in. So if I have the CPS, which is where they figure out the unemployment rate, I don't know anything about people's height, which people get paid more if they're taller. I don't know anything about their, how they look, about their non-cognitive skills, about their cognitive skills, about any of it, okay? If I think that schooling and skill are positively correlated, that is that, people with higher levels of all these skills that are rewarded in the labor market also find it easier to get more schooling, then I would expect there to be bias, okay? And I would overestimate the effects of education on wages because I wasn't controlling for this skill measure, okay?
Question, Marianne. So
Sure.
practically, I'll say what at least I and my team we often do is try to think about the bias, mainly so if it's a conservative bias, we can kind of say that in the paper that we consider this and we believe this analysis is conservative because the bias would take us towards the null. But I guess are there other reasons why, practically speaking, we should think through this issue of direction of the bias?
Well, I think the simple case that I'm giving, like it's easy to see which way we think the bias is probably going to go here. But suppose instead of just, suppose there were other factors that mattered for education in different ways besides just skill. So it wasn't a unidimensional thing. You could have biases upward and downward that could matter. And once you add on, I'm not going to really talk about measurement error today, but depending on how you think the measurement error works, when it's non-classical measurement error, you also, can get bias that goes in perverse directions. And so I think both of those, having a bunch more controls that could be correlated with whatever's omitted, and also issues with measurement error, make it a harder story, even though I always do think it's worth talking through if you really think you can figure out what is the key omitted variable.
Mm-hmm. Sure.
But I think there are settings where, if you want to think about welfare, right? If you want to figure out a cost benefit analysis, sure, if you knew it was conservative, that would be great, right? But that's if that's the only uncertainty that's in your thing, right?
Yes.
So I think that's the other reason why you sort of care about getting or trying to having the goal of consistent and unbiased estimates. And so then I had another example for private health insurance and health. So income and resources are omitted and they're positively correlated with health and they're positively correlated with private health insurance. Then again, we think that the bias term is going to be positive. Okay. We're going to overestimate the causal effects of private health insurance on health. Okay. Here's my example for simultaneous causation. Okay. So Y affects X. So this equation is the true population, relationship between Y and X causes Y. So this is the true population value for X and Y. So if the error term here is big, that means a big YI, which also means a big XI. So then the correlation between XI here and this error term can't be 0, and you're going to get bias. Okay, and I'll fix these and send them back. Sorry about the betas not being right in my efforts to do this in LaTeX quickly at the last minute. Okay, so here, and this is my example I already gave you for health and having a job with private health insurance. If you have poor health, you can't work, so you don't have private health insurance. But people with private health insurance will have better health because they could have the money to purchase the private health insurance. And so you're going to get a correlation between the error term and the health insurance. Okay, so instrumental variables offer a solution to OVB and simultaneous causation, and they can also help with measurement error. They don't really help with these issues of improper functional forms, but I was trained to keep it simple, so I'm sort of do what many statisticians don't love, which is use linear models for most stuff. I would say in practice, it doesn't seem to matter a whole lot most of the time, but that's not an attractive stance from the perspective of a bunch of statisticians. Okay, so the goal is to find an instrument, Z, that only affects Y through the variable D. Okay, and so the simplest example is an RCT. If I'm randomizing an offer of treatment, and the only way you can get the treatment is if I offer it to you, and then you choose whether you're going to participate in it, and I'm worried that you might have chosen it because you know something about, there's something about your knowledge or, you that makes the people who choose D equal to 1 if I offer it to them, that's different from the people who choose not to take it up. Well, pretty clearly, if Z is randomized, then the only way Z can be affecting Y is through D, right? Because there's nothing else, there's no other pathway for Z to affect Y. Okay, so a concrete example of this that I'm sure you guys are all familiar with, but this is just meant to remind you of examples you already know about, because that helps you think through this, is the Oregon Health Experiment. So in the Oregon Health Experiment, D is Medicaid take up, right? And so the way this worked is they didn't have enough money to expand Medicaid to everyone in Oregon amongst a somewhat elderly, somewhat chronically ill population. So they were getting Medicaid not because they had kids or anything, or they were pregnant, but because they were low income and had poor health. And Z was this lottery offer of Medicaid. So you could sign up, you could apply, and then amongst the people who applied, they randomized it. Okay, so Y can be a whole host of outcomes. They've written like 15 papers on this, but it's hard to come up with anything about the lottery offer that should affect any of those outcomes, except if it's working through Medicaid. Okay, and so let's see, this is, I think I said all of this. Okay, so the key thing here is when you run this, the first thing you do in these models is you run a first stage, which in the case of this example is I'm going to regress Medicaid on whether you got an offer of Medicaid. That's called the first stage because there's a way in which you can do this as two separate models, predict the D hat, and put that in the second stage, and you get the same thing as if you do this thing called two-stage least squares. But the important part is if I regress D on Z, then predict D hat, the only part of that I'm getting is the part of D that is correlated with Z, which was randomly assigned. So all the bad parts of D are in the error term then, because it's a linear model. And so then I'm only taking that good part of D that's correlated with Z and putting that in the second stage. So if you think of that as what two-stage least squares is doing, it's pretty intuitive why you're getting rid of the problem. The endogenous or bad part of D is going into the error term in the first stage, and you're not including that in the second stage, okay? Importantly, then, the next step is to think about whether D is constant or D has varying effects, okay? So if D is constant, then this effect you get is the effect for everyone, okay? Otherwise, it's the effect on average for the people where Z is changing their value of D, okay? So now I'm going to talk through this in the basic linear IB setting. So there's Y, D is endogenous. There's a whole bunch of other X's that are there. You can think of them as like in a normal experiment, you would control for other X's to sort of, reduce the overall variation and get more precision on your key coefficients of interest. But importantly, you want these to be exogenous things. And you're worried that D and the error term are correlated. So you're going to get your instrument Z. And there are two things you have to check. You have to check relevance. So there is a first stage. So if I regress my endogenous variable X1 or D on the other X's and Z, I need to be sure that the coefficient on Z is not zero, and that it's quite a strong relationship statistically. Okay, that's called the first stage, and the key first stage statistics I'll tell you about in a little bit. And then the second part is something you can't really test. Okay, which is that Z only affects Y through X1, okay? And I can only argue for this. So in this case of an experiment where I'm offering health insurance, I think it's an easy argument, right? It's hard to see how if I offered you randomly health insurance and you choose to take it up, how could my offer have affected you otherwise? But in lots of other settings, there might be a problem. So one that there's a lot of discussion about in development economics is there's many papers that use rainfall as an instrument for something. And there are concerns that, rainfall affects a lot of things, and it might not only affect whatever it is through the pathway that you're imagining, okay? I'm going to give you another example. Suppose Y is my outcome of interest, S is schooling, so we're back to my labor economics example, and Y is going to be earnings. So then the error term here is a function of ability plus something else, okay? And I'm going to assume the only reason that the error term and schooling are correlated is because of the ability. So this other part of the error term here isn't a problem for me, okay? So if I knew what ability was and I put it in this regression, then I'd get the right coefficient row on schooling. But if I don't see the ability measure, which again, I think it's hard to imagine you could really measure all the things that are rewarded in the labor market, then there's no way I can be sure, unless I'm willing to assume that this doesn't matter for wages, I'm not going to get the right value. Okay. So if Z is an instrument, then the easiest thing you could do is something that's called the Wald estimate. Okay. And so you can just calculate rho as the correlation between Y and Z divided by the correlation between S and Z, which you can rewrite this way. And so you can see that this is the ratio of this thing that's called the reduced form, which is the regression of Y, the outcome, on Z, the instrument, and you divide it by the first stage, which is the regression of S, the endogenous right-hand side variable, on Z, the instrument, okay? And sometimes people will even calculate these in different data sets and take the ratio. That's called indirect least squares.
One
okay?
quick question here. The S variable there, that's the coefficient on the Z from the first stage, is that right?
No, S is the endogenous variable years of schooling. And in
I see. Okay.
the setting I'm going to tell you about is this famous paper by Josh Angrist and Alan Kruger, where they're interested in how schooling affects wages, because labor economists are obsessed with that. And they find this feature of schooling in the 50s and 60s that, because of the way everybody who's got kids knows you're supposed to sign your kid up for school. In California, it's the year that they turn 6, they have to go to school. And if you're born before September 1st, you go to school in the year when you are already 6. And you're not yet 6. And if you're born afterwards, you go to the school in the year when you are 6. And so if you're born relatively later in the year, you start school when you're older. And so you can drop out of school when you're older because the dropout rules all have to do with turning 16. They don't have to do with a particular number of years of school. And so they saw this empirical regularity that, there were these differences by quarter of birth and how much schooling people got, and there were differences by quarter of birth in their wages. And so, this was one of the first papers that uses this kind of strategy. And they could do it even in just these these simple like indirect least squares way. So they could just look at, compare wages for people born in Q1 versus Q2s through 4 and divide that by schooling completed for people born in Q1 versus Q2 through 4. Okay.
So it just has to be some sort of observable variable there. if you were to apply it to other examples.
Yes, you want Y to be your outcome, you want S to be your endogenous variable, and then Z has to be something that you see.
Okay, thank you.
So like, and I'll come to where we find instruments if you don't run your own experiment in a little bit, okay? And I think I said this, all right, and I said it was causal, so it's relevant. So in my example of schooling and wages, it has to be that people who were born in Q1 have a different level of schooling than people born in the other quarters. That's easy to test statistically. And then it has to be excludable, which has two parts, but really it just means that you have to have this feature that the only reason that there are differences between people born in Q1 and people born in Q2 through 4, the only reason that difference matters for outcomes is because it affects their schooling, okay? And, people have raised other reasons why it might be differences for people born in Q1 versus born in Q2 through 4. That's why a lot of people have moved towards mostly trying to use experiments or true random things, and not like, because there's evidence that people born in Q1's parents have different characteristics than people born in Q2 through 4. Okay, so these instruments, great, they give you this fantastic, unbiased and consistent estimate of the thing you care about if you can find them. So the best case is you find your own experiment and then you have instruments, okay? But a second example that's really common is something that's called, it's common in regression discontinuity designs, which I'm sure you're all familiar with, right? In regression discontinuity, there's some feature that assigns eligibility for a program or assigns a program to people whose score is above some amount. So think about the National Merit Scholarships. That's the first example of this approach. The National Merit Scholarship, if your PSAT score is above a particular point, you're eligible for this scholarship. If it's below that point, you're not. It's in theory graded fairly. And so, for people who are very close to the cutoff, the difference between being above and below the cutoff is random. And so that provides a first stage in that you're only eligible for this thing if your score is above a particular point, okay? So many programs have a feature like this. In a lot of, like, for Medicare, when you turn 65, you're eligible for Medicare. For the WIC program, the program ends when you turn 5, but there are lots of other things where there's either a score or there's a age or there's a time variable that determines this. So often program rules can serve as an instrument. There's this idea of simulated eligibility in the Medicaid program that you guys may have or may not have seen, where you sort of figure out, given program rules, if I took the whole population and ran them through the rules in the state, how many of them would be eligible? That abstracts away from the characteristics of the people in the state. And then there are things like true randomness. So birth timing, in some settings is viewed as quasi-random. So clearly you can delay or speed up birth timing a little bit, but not very much. Gender mix before infertility treatment, if you didn't have stopping rules, could be random. Twinning before infertility treatment was random. It's not random anymore, or, but it was random at some point. I mean, it's like correlated with being older, and Black people have higher rates of twinning. But so these are the sort of things people use as instruments. And like I said, in development economics, they use RAIN, but that's gotten a bit of pushback, okay? And then for other problems, there's something that's called a shift share. So in something like understanding the effects of immigration, it's very hard to, so if you want to understand what having an inflow of immigrants to your area does to people who are natives who already live there, that's a very hard problem, right? It's hard to argue that that's random. It could be that people move to your area because there are a lot of jobs. And so, that's reverse causality, and you wouldn't be actually estimating the real effect of the immigrants on the wages for the other people. You'd be seeing the fact that good wages for the other people led immigrants to move there. And so this shift share design says, well, in the case of immigration, we think people move to places where other people like them live. And so in this setup, you would say, figure out what share of the particular group of immigrants you're interested in lived in your place in 1960. And then you would combine that with a national change in immigration. And that'll give you a shock of immigrant supply to your area that's not contaminated by these labor demand features. And people use this for other kinds of questions as well, but that's one example where it's hard to get good exogenous variation. I mean, because people sort to places intentionally. And there are lots of other examples of instruments, but this is just a flavor of what they are. And so for your particular problem, you might want to think about the features of the program as it's run, or what eligibility for it is, or geographic differences. I'll give you a couple examples of some work of my own that uses something about the fact that in California, the SNAP program is run at the county level. And so some county policies can be used as an instrument. So two classic papers on IV. Josh Angrist has a paper on the Vietnam draft lottery, which was, apparently it wasn't fully random, but they didn't learn that right away. And so if you got a lower number, you were more likely to get drafted. And so, you could instrument for the effects of being in the military with what your draft number was, to get a causal estimate of what the effects of having been in the military are on your earnings when you're older, or your health. Okay. And then this compulsory schooling example with also Alan Kruger, which I already exampled. Okay. And I think I already said this, so I'm going to skip this, but you will see this. And one important thing to know is with this example, as I said, he's figuring out the effects of leaving school around 10th grade. So it's figuring out for people who their birth date means they stay in school till 10th grade, or they drop out in 9th grade. Okay. That's what the instrument in this compulsory schooling thing is. Okay. And so it's not going to be informative for telling you about what getting a PhD does. It's only going to be informative for telling you, for the kinds of people for whom telling you you can't drop out yet matters for how much schooling they get. What does it do to their wages? Okay. And so that's one important thing to remember, is that these policies, unless you assume everybody, the effect of a year of schooling is the same for everybody at every level, you're only getting estimates that are meaningful around this area where the variation is coming from, unless you're willing to make a lot of assumptions. Okay. Something that I think is really powerful in some of these, in this particular paper, but in some IV papers, is sometimes it's really simple to draw the first stage and draw the reduced form and see that the variation. So I didn't put it here because you guys don't care very much probably about the effects of dropout rules on schooling. But the thing that's cool about this paper is when you look at the wages plotted by quarter of birth, you sort of see this sawtooth pattern, and you see the same thing for completed schooling. And so I think it's also nice when you can see the raw data supports your identifying variation without having to control for a lot of things. The RD papers also tend to have this flavor, so if it was age, if you were thinking, I'll get to it in a little bit, I'll show you an RD example, and you'll see this point that you can sort of see it in the raw data. Oh, it's right here. Sorry. So David Card, Carlos Dotkin, and Nicole Mastis have a 2008 paper, and I'm going to show you a couple other slides from their paper, but basically, as you all know, eligibility for Medicare kicks in at age 65, and they're going to do this regression discontinuity. So they're going to compare people who just turned a little more than 65 with people who are a little under 65. And if nothing else important changes at 65, if you control for age flexibly, then any other changes you see have to be the effect of having become eligible for Medicare. Okay, and so I'm going to go to my other slides here. So this is a graph from their paper in the AER. And so the x-axis here is age in quarters. Okay. So here is the discontinuity at age 65. Okay. And these are a whole bunch of different measures of having any insurance or two or more policies of insurance by age and demographic group. Okay. And so the squares here is any coverage for high education whites who are extremely likely to have private coverage before then. And you sort of see, even for them, there's a little bit of a change, but it's not very big. The diamonds here, where I'm sketching out, that jumps up here by, at least 12 or 14 percentage points. That's any coverage for everybody. So overall, there's on the ballpark a 10 or 12 percentage point increase in the probability of having insurance coverage. And then, no surprise to you guys, any coverage for low education minorities goes up a lot. And you also see this effect, the big effect for the high education whites is they get a second form of insurance. Okay, they go from having one form to two forms. So either employer provided insurance before and Medicare plus Medigap after, or employer provided before, employer plus Medicare after. Okay. So this is just plotting the means for these age groups, and you can see it's very transparent where the variation is coming from here. Okay. And then these regressions are regressions of a whole bunch of health outcomes that, what the change is at a particular age. Okay. And so this is the so-called reduced form. So if I were to take this example, overall, if in the NHIS in these years that are identified here, 7.2% of the people who are 63 or 64 delayed care last year. And there was a reduction in that at 65 of 1.8 percentage points, and it's statistically significant. And you can sort of see, if you look across some different gradients that you might expect, you don't always see the pattern that you would expect. But if I look at, if I look by race, you can see a 1.6 percentage point decline in having delayed care last year for white non-Hispanic folks, a 1.9 percentage point decline for Black and non-Hispanic folks, and a 4.9 percentage point decline for Hispanics. And you see sort of broadly similar findings with the gradients that you might have expected, given the other side, given the first stage as well, for not having care last year, having seen the doctor last year, and having hospital stays last year. Okay. So then the instrumental variables estimate of this is just going to be the ratio of this reduced form divided by the first stage. Okay. And then finally, the thing that they did in this paper that's interesting is sort of think about different kinds of things where, economists, so moral hazard. So of course they're looking to see, is this is it emissions that were necessary and not things you could put off until Medicare could pay for them? Or was there a suggestion that people were waiting to get things done that they couldn't afford to get done? And so the first thing they do is look at all emissions here, and you sort of see an increase in all emissions, but then you also notice that there is a non-trivial increase in the probability of hip and knee replacements once people are eligible for Medicare, which I'm sure makes them better off, but might not be like the best. It might be nice if you could figure out who really needed it and not have it be all paid for by Medicare. Okay. Another thing that people have used this 65 threshold for is changes in financial security. So the idea being that when you have Medicare, you're insured against really big health losses. And they do this using both the MEPS, where they find a decline in out-of-pocket spending, and I think they do some stuff in the HRS too. Okay. So that's just some examples of one of these where it's really pretty straightforward to show people the variation and understand where it's coming from. Okay. So I think, and they also, they're all also clear proof that being eligible for Medicare is better in terms of mortality and stuff. So it's not all just this like delays in care that you might be suspicious of. Okay. Here's our example from the Oregon health insurance experiment. So I just pulled one random outcome that was one of the first tables in the science paper. So in this example, Y is emergency department use, D is Medicaid take-up, and Z was the lottery. So remember, they sent out mail to a whole bunch of people and said, sign up if you want to be eligible for a lottery to get Medicaid. And then they randomly drew it, and the tables look balanced. So it looks like the lottery was correctly assigned. In the first stage, they found that people who won the lottery had about a 25 percentage point increase in the probability of being on Medicaid at all over the time period. And then in the reduced form, the people who won the lottery were 1.7 percentage points more likely to use the ED. So the IV estimate, again, in the simple case where it's really like an experiment, is 0.017 divided by the 2.46, or a 7% effect. So Medicaid here leads to a 7 percentage point increase in using the ED. And my recollection of this paper is it's sort of evenly split between urgent things where you have to go to the hospital and other kinds of visits. Okay. And they go on to look at a whole host of other things that I'm sure you guys are more familiar with than me. But I like to use this one when I teach the undergrads because it's really, it's straightforward to explain. But I'm using it for you guys because it ties back to our original example. Okay, and then I'll just give you another example of some recent work of mine. So as part of the same stuff that was presented at this meeting, although mostly I was talking about something else, we're evaluating the cash out of the SSI program. So SSI is a cash transfer program for low-income, disabled, blind, and elderly persons. And in most states, but not California till very recently, if you were on SSI, you could also receive food stamps or SNAP. California changed this law so that as of 6/2019, people on SSI suddenly could also get SNAP, but before that they couldn't. And in a variety of ways, we're trying to evaluate this. So one instrument that we're thinking about using is related to county outreach plans. So as you guys may well know, counties in California have some control over welfare programs. They're run by the counties rather than by the state entirely. You know, the state obviously has some effect on how they run them, but the counties themselves kind of make some choices about things. And so when this news of this program change happened, counties set up outreach plans about what they wanted to do in terms of reaching out. And so it could be things like, you know, newspaper ads, social media, calling people, postcards, etc. Okay. And so our idea is to interact when you could actually get the new program with the characteristics of the county outreach plans and the number of county outreach plans, and then control for other stuff about the county. Okay, and so the first part about thinking about this is this instrument relevant? Does it affect, do these county outreach plans interacted with the policy being available actually affect take up? And it looks like it does in aggregate data. And then the second piece is, does it, you know, and it has to do it strongly enough that you can actually, you know, be able to use it to figure out what the effects of getting SNAP on health are. So that's a little bit trickier, but it seems relevant in the regressions that we've run. So then the second question is, are you worried that there's a violation of this exclusion restriction? And I would argue, no, it's hard to see how county outreach to people on SSI telling them they're eligible for SNAP would affect anything but use of SNAP, you know, could affect anything except through use of SNAP. Okay, but you know, you have to decide for yourself whenever you hear one of these papers, does that sound believable or not? Okay. And so I'm going to summarize this first part of the talk, and I have a little more to say after this about do's and don'ts. But you know, first thing, we talked about constant effects, and now we're going to worry about time person varying effects. Okay. And so that's this idea of a local average treatment effect. That's the idea that I might have a different response to a treatment than somebody else. And so for the set of people where things get changed, I'm going to be estimating an average for them. Okay. And I think this is where most, you know, most economists think about IV in this way today, or at least the economists who are like me do. Okay. So we've already talked about this part. There's a whole bunch of assumptions that are not super important, with the exception of one assumption that I'm going to tell you a little bit more about. Okay. So, you know, you need a first stage. So you need that somebody gets moved into treatment by the instrumental variable. And then importantly, if you can assume this thing called monotonicity, that is that the instrument moves everybody in the same direction, then you can derive something important about what the findings are. Okay. And so what this means is, you know, different people can have a different response to the treatment, and different people can have a different first stage, but it can't be the case that if you know, being offered the chance to sign up for Medicaid makes some people sign up for Medicaid. It can't be that there are perverse people out there who would get Medicaid if they weren't offered it, but won't sign up for it if they are offered it. Okay. So that's called excluding defiers. Okay. And so what this means is, you know, if I'm offered the treatment, then either my probability of being treated is bigger than my probability of not being taking it up if I'm not treated. Sorry, I said that backwards. My probability of taking up the treatment if I'm offered the thing has to be bigger than taking it up if I'm not offered it for everybody, or it has to go the other way. Okay. Now there's some discussion about this, like Heckman and folks think that this is not a very appealing restriction. Okay. And there's work to think about this, but you know, in most settings, I don't think this assumption is so difficult. One example where it is a problem is something like red shirting. You know, so some people want to send their kids to school early. Some people send their kids to school on time. Some people redshirt. You know, it's easy to come up with examples where that violates this monotonicity. Okay. And in this draft lottery example, you know, you can't have anyone who, if they got a high draft number and wasn't going to get drafted, they serve, but they wouldn't have served if they got a low draft number. Okay. So if that's the case, then IV gives you a weighted estimate of this individual causal effect. Okay. So this instrument would be a mix of complier and defier estimates. Unless you're willing to assume this monotonicity, then there's no defiers and it's only an estimate for the compliers. Okay. So you guys don't need all this math, but it doesn't matter if you have constant effects, because then the defiers effect and the compliers effect is the same. Okay. The other thing to know is when you have this thing about compliers, unless everybody is a complier, there are some groups you don't learn very much about. You don't learn anything about people who would use the treatment all the time, and you don't learn anything, you call them always takers. And we don't learn anything about the treatment effects for people who never participate. We call them the never takers. Okay. So this experiment can only tell us about people who are on the margin of being moved by whatever the experiment is varying. And this is a more interesting population, these compliers, the bigger the first stage is. So if you can, you know, keep anybody from getting the treatment unless you offer it to them, then there's no always takers. And so then it's a more interesting estimate. And if you can be sure that there's nobody who's a never taker, it's a more interesting thing. So this is why the folks who run RCTs want to have a really big first stage. Because if you had everybody as a complier, then that would be great, because then you would get the average treatment effect for everybody, as opposed to just for the compliers. Okay, you can also get characteristics of the people who comply. From results are in this paper here. It's pretty easy to do. And then just some to-dos and not to-dos, okay? So the first thing that's important is you need to put any other controls that are not the, you know, suppose I want to think about my example of schooling and wages. Any other controls I put in the model, like gender, I have to put in both stages. Otherwise, I'm not getting the right thing out of it, okay? So the way to think about this is I have my instrument for my endogenous variable, D, and then the exogenous variables are instruments for themselves, okay? But you have to put anything you want to put on the right-hand side for the first stage, you need to put in the second stage. The second is, if you're talking to folks who are concerned about using a linear model for a 0-1 variable, so you have an endogenous right-hand side variable, and you decide you want to estimate d hat and put that d hat in the second stage, that's not going to work anymore, because the niceness about two-stage least squares comes from the fact that you're using a linear model. So when it's a non-linear model, you don't want to do that anymore, okay? And then there are some challenges with what's known as weak instruments. So if Z only affects D a little bit, it can cause a problem. So we learned this in a paper from Bound, Yeager, and Baker. So Bound was and Yeager, two labor economists. Baker was some student who took the class with them. And the concern is, you know, if the IV is weak, then you can get inconsistency, okay? And so what did they do to show this? They made up birthdays for people from the census, and then they ran regressions. So they randomized people's quarters of birth, and then they pretended they were real quarters of birth. And then they estimated models like the ones that the Angrist and Kruger paper had estimated. And if they just used the quarter of birth, this didn't cause a problem. You got garbage when you used the random noise, and you got real estimates when you didn't. But if you interacted quarter of birth with state of birth, you start to get a lot of instruments, okay? So then this first stage isn't very strong, because the F statistic that's relevant is the partial F on all the instruments in the first stage. And if you use this garbage interacted fake birthdays with states, you got garbage. And it didn't even look like it was like noisy garbage. It looked very much like the real estimates, okay? So I'm not going to show you this, but the point is there are some ways that fix this, but you really want to focus on having strong first stages. Okay. And this article is about weak IV and talks about some other suggested things to do when you have weak IV, which is a big problem in a lot of, economists' IV papers, because economists are struggling to find instruments that really move stuff very much. So they like to interact it with other stuff, and then you get this IV problem, okay? So the point that they make strongly in this paper that I think is, so first of all, it makes a suggestion about what you can do for heteroscedasticity and what you can do when you have more than one instrument. But it also points out that you're going to get, you have a pre-testing problem if you just, use weak IV methods only if you fail the first stage. So they have some suggestions about that as well. Okay. So then that is what I had prepared. I think I'm done a little bit early, but that leaves some time for questions if you guys have it. And I will clean up the typos in the slides and send them on to you.
Terrific. Yeah, thank you so much. And we look forward to getting them to sit and go a little slower, make sure we all catch it. But this has been great. And I think, Richard, you can go ahead and ask your question. I have the same question, but you can ask it if you'd like out loud to Marianne.
Yeah, thank you so much. I was just asking, when you're talking about the problem with weak instruments, what F statistic you use as a cutoff in the first stage, like 15 or 20, or what do you recommend, or do you have a rule of thumb for that?
So there's a rule of thumb that people used to use, which was 10, but I would go and I would use this, if I had one instrument, I would use this Olia and Pfluger number, and they have some guidelines about what the right number is for one, for two instruments, for three instruments. And, it reduces to this Kleiberger PAP test if there's only one IV. But if you have a number like 60 with one or two instruments, you're probably fine. 10 is probably not the right number. And part of what they do, I think, is they plot things. They plot the number of papers by the F statistic. And you sort of see all this clumping at 10, because for a long time there was an older Stock and maybe Watson paper, Stock and Hugo paper, where they sort of suggested that you use 10. Given some assumptions. And then there's a more recent paper you might have seen that sort of talks about that 10 number came out of some kind of error that you were willing to accept. And if you wanted a finer control on that error, you needed a much bigger number. I would say practically in experiments, I don't think the first stage is ever a problem unless you get really unlucky. It's more when you're sort of using observational data and you want something that really moves it. And I think that's part of what has led to this big change towards mostly seeing experiments and then, things like program rules, like RD kind of strategies.
Great. Thank you so much.
Sure.
So any other questions?
Yeah, I had a question. It's more of a practical question. So at which point in the research process do we need to start considering instrumental variables? Is it something that should happen during study design, or something that comes up after you've collected data and a reviewer brings up that you might have some omitted variables? Obviously, these are not something that I encounter in my research, so I'm very naive.
So I think if you have the ability to randomize some piece of what you're doing, then I think that's the best of all worlds, because then you're sort of protected against this. But obviously, I do a lot of research on the WIC program. If you try to tell a bunch of WIC folks, let's deny people something that we think is good for them, that's a little hard to get people to sign on to. So that's why a lot of the, I probably should have listed it separately in my list of IVs, but waiting lists are a great instrument, when something is oversubscribed, because then all you're saying is, you're not saying keep people from getting this when you have empty slots, you're saying it's oversubscribed anyway, so let's randomize who gets it. And people are okay with that because that feels more fair. So I think if you can, at a minimum, think about, with whatever your design is, as Kenrick was saying, try to think through which way the bias, if you take a simple view of what is driving it, or if you, which I think is the right approach, think about the simple version of what the bias is from, which way is it going to go? Is it going to mean that you have an underestimate of the thing that you care about in magnitude or not? If it's an underestimate, usually that is enough to at least be interested in. But I think there are lots of problems where it's really hard to imagine what a good instrument would be. So, I wouldn't quite go this far, but I think there are some people who think if you find an instrument, then go find some outcome that it's interesting to use to look at, because it's going to give you this clean variation. And I think maybe I thought more like that when I was younger, and now I'm more interested in the findings than I am. And I'm a little less obsessed with the methods than I was when I was 35, I'll say. But yeah, if you can't, there are also other kinds of partial identification approaches, and there are other ways to deal with these kinds of problems.
So I think, Rock, you have a question if you wanted to ask.
Yeah, thank you so much for this great presentation. I was just wondering, I know there's a lot of talks about finding the right instrument, and not everyone always agrees that one instrument is better than the other. I was wondering if you have some ideas of maybe if there's a repository or a paper that sort of summarizes in terms of, by strength, the best instrument that we could use so that we can apply it to different fields. Because I'm in epidemiology and health services research, and so I'm always trying to find good instrument for my studies. But it doesn't seem that there's a lot out there. So I'm just wondering if you have any ideas of how to best go about finding the best instrument.
I mean, I think best is a little bit in the eye of the beholder. So I'm someone who's really interested in policy. And so for me, policy variation is the interesting instrument, because it's like the action items that are available to the person who's setting things up. But I think, again, if you can randomize something about your setting and you can do it and you have some idea that people are really going to respond to the randomization, so there's lots of failed experiments because people didn't respond. I have an experiment where we're trying to nudge women who use a pregnancy tracking device. We're trying to nudge them, if they're pregnant, to get on the WIC program. And, we have really big samples and it's a 0.00000. So that's not it's depressing, right? I mean, but maybe it adds to how not to nudge people. But I think on the other side, the other things you should care about are how clean is the exclusion restriction, and how strong is the first stage. Those are the other features. And I guess the other things besides the stuff I've mentioned that I also see a lot of are in programs where either eligibility or something else is decided by agents, and there are lots of agents, then you sort of see these judge designs. So, if you want to figure out what the effect of getting bail is, that'll be one example I can think of right now off the top of my head. There's a bail judge, and so depending on the bail judge, you get assigned no bail or a lot of bail. So then you can use the average probability that the judge gives people bail who aren't you as an instrument for whether or not you're going to get bail or not. And I think those findings find getting bail is bad for you. But anything where there's these judges, there's a lot of agents who are making choices. So this has been used for criminal stuff. It's been used for getting disability insurance, because there's these administrative law judges who decide that. One of my co-authors is using it to try to understand for caseworkers. It's been used in the case of child foster care to sort of see if taking kids away from their family members is better for them and putting them into foster care versus letting them stay with their family members where there was a problem. But for that, you often need administrative data and many agents making choices. So that's the other example that I think I see a lot. So along with the other ones that I suggested.
Thank you so much. This is great. Thank you. Appreciate it.
Great. So I think we're at time, but Louisa, you turned your camera on, so maybe you can close us out if you have a question or a thought.
Oh, I'm another economist, and I was telling earlier that, I'm very excited. The lecture was so helpful. So thank you so much. I have these jokes that I remember, that whenever you present, they will ask, well, have you found a good instrument, right? I mean, I feel like all the economics seminars will end with that, right? You need a good instrument for that, so I think, the way you presented was very good. And yeah, I love your insight at the end, right? How do we find good instruments? Well, we'll probably need to figure out how we can randomize, right? And if not, we need to get really creative, right? So thank you. I really appreciate it.
Sure thing.
Yeah, thank you so much, Marianne, for giving us your time, and we look forward to getting the slides. We really appreciate it, and I guess I'll be talking to you soon in our network, Carol and I.
I'm
But,
I'm sure. I look
yeah,
forward to it.